Welcome to International Biorenewables Law and Policy. This presentation is focused on the biorenewable supply chain and the uncertainties of several factors in the supply chain. As an overview, the purpose of the biorenewable supply chain is to provide consumers with renewable products generated from biomass. In order to do this, there are several steps that are required, and we're going to go through some of those steps in this presentation. As you can see in this slide, the supply chain can be divided into three major steps. We start with agricultural farms, which produce biomass and supply it to the biorefineries. In between these two steps, there's a logistics step where the biomass is transported through a network to said biorefineries. The biorefineries then converted or manufacture bioenergy products and chemicals. Those eventually need to be transported to the end user, which in the case of biofuel might be a gas station or other type of consumer station. In order for the supply chain to operate, the biorenewable enterprise plays a major role in deciding the structure of the supply chain. A company invested in producing biorenewable products will need to choose what type of feedstock they need for their facilities and how much of that feedstock. They'll need to choose a location for that facility, and then they typically have a given market that they're targeting, either in terms of the products that they produce or specific consumers that might use those products. In the work by Awudu and Zhang from 2013, there's a detailed description of a typical biorenewable supply chain. In their analysis, they look at the conversion of one type of feedstock, in this case corn, into ethanol, corn oil, and dried distillers grains. The final products are sent to distribution centers for end-use markets. This topology diagram shown here, similar to the previous one, shows three different layers. Within those layers, you usually have a large network of suppliers, a smaller but wide range of biorefineries that compete for the biomass available from the suppliers, and several markets that consume the products generated by the biorefineries. And when you try to optimize a system like this, there are several parameters that are required to understand. That includes prices for materials, it includes distances, it includes which connections to make, so which facility will buy biomass from which supplier, and which distribution center will receive products from which refinery. And so Awudu and Zhang developed a fairly common modeling mathematical formulation that try to estimate the cost of producing this product in the supply chain. We'll start by looking at some of the decisions that have to be made. The first one is site selection. So biorefineries need to take several factors when they're picking a selection or a site for their facilities. These include feedstock availability. This is not just how much biomass is grown, but how much biomass will growers be willing to provide. So it involves taking surveys of local farmers and producers. Regional infrastructure, are there sufficient roads to move the biomass? Are the roads in good shape, or do they have to invest in upgrading some of the roads? Labor market, is there sufficiently skilled labor market around the facility, or would they have to bring in workers from other regions? Market accessibility, how far do they have to go to deliver their products? So these are just some of the many decisions that go into determining where should they locate the facilities and what types and size of facilities should go in those locations. In a study by Zhang and myself, we looked at a fast pyrolysis facility trying to find locations in the Minnesota state. And to give you an idea of what these models can generate in terms of how facilities locate themselves and how they gather biomass, this figure here shows how several facilities, 5 or 6 facilities, were sited within the state to utilize a portion of their available biomass. The triangles of different colors indicate the size of the facilities, and the arrows indicate where the biomass is coming from. And the biomass can either be raw biomass, shown in green, or it could be pre-treated biomass that has been chipped and eventually shipped to the facility. All these fast process facilities produce an intermediate product that they send to their final consumer, which in this case is a refinery facility, and there's a refinery facility located towards the central eastern region of Minnesota in Pine, Kennebec. And so these mathematical models are often fairly good at determining what the optimal locations are for a set of facilities so that they utilize the biomass in a equitable and profitable fashion. However, in practice, biorefineries don't usually coordinate this well, and so you're going to find regions where there might be competition for a limited set of resources. And when you have competition, then you have to look at feedstock supply and demand, for example. When you have a supply-demand dynamics, what you end up finding are that producers want to supply biomass at a given price, while biorefineries want to purchase the biomass at a different price. And so what price is ultimately, the biomass is ultimately sold for will depend on the market power of these two agents. So for example, in a producer market, producers will try to sell the biomass for as high as possible, or as high as the biorefineries will tolerate without hurting their profits. In a market where the biorefineries have the purchasing power, they will try to lower prices to as far as they can go without affecting producers' ability to deliver the biomass. These two market power scenarios occur often, and they're often driven by the differences in competition within a given region. Obviously, in a location where there's a lot of competition between biorefineries, that might be advantageous for producers who can provide feedstock to the highest bidder. But if you only have a single biorefinery or very few biorefineries, then producers may have to deliver the biomass at the price demanded by the biorefinery. However, in addition to regional availability and competition, there are other factors that can influence the market power. So both producers and biorefineries could have an advantage of coming up with contracts that may not give them the maximum profit, but gives them reduces their risk over time. Market dynamics, for example, if you have a major climate event, that will certainly change the availability of feedstock and result in higher prices or more competition for feedstock. And so when looking at or analyzing a supply chain, it's very important to understand the uncertainty involved with several factors, and that's part of what the paper by Wudu tries to do. What we're showing here is an example of the variation of different material and energy prices that have been found historically. So certainly we know that the price of gasoline and diesel has varied significantly in the last few decades. And ethanol, not to the greatest extent, has also varied quite a bit. Natural gas is not historically low prices, but you can see here that at certain points in time, it's been more than twice the price that it has today. And even something like feedstock, when you look at pine pulpwood prices in the southwestern region, what we found is that the price of the delivered pine can vary significantly depending on how far it's transported, how much is available in the region, and other factors. So biorefineries and supply chains often need to consider uncertainty in their decisions, and they often try to mitigate uncertainty by using several tools. So for example, you can develop long-term contracts. You can purchase insurance to guard against extreme swings in prices that would erode profits. You can store some of the materials like biomass long-term so that you only have to buy biomass when it's at a reasonable price. And so these are some of the short and long-term considerations that biorefineries take into account when they decide where to locate their facility. The impact of this uncertainty can be seen in the expected price. And so Awudu shows his results, or their results, in two ways. One is by calculating the mean, which is the dashed line, and the other one is what they call the geometric Brownian motion or random motion of the price. Now, in this particular case, the mean seems to be skewed away from the 1,000 step line, and that is because in some of their scenarios, they're getting some very high expected values for their ethanol price. However, as it's shown here, they look at most of their prices are between the $0 to $5 per gallon range, which is typical of corn ethanol prices. In terms of the profits that the supply chains generate, you can see that when you add uncertainty to a model or the analysis, it's going to lead to a significant change in your expected price or expected cost of producing that biorenewable product. And so in addition to the decisions that biorefinery enterprises can do to mitigate uncertainty, sometimes we need market and policy tools to help alleviate the risks of operating these facilities. And so that can be done through incentive programs, market prices, and other types of risk aversion policies. So to conclude our discussion on the supply chain, we'll just recap some of the things we mentioned. There are several steps involved in the conversion of feedstock to end-use products, and the enterprises have a major role in determining how the biomass or what types of biomass are converted into these products and what is the structure of the supply chain that delivers those products. However, there are significant uncertainties in the supply chain, and so it's very difficult to estimate the expected cost and prices of the biorenewable products because of all these different variances in prices, availability, and decisions.